So are you guys able to see my screen? Someone to confirm that you're able to see my screen? Good. So as I was saying that I think the example that you were doing on Thursday, it was quite complex. So I just decided that we are going to start with a simple example, and then you're going to get to the one you were doing on Thursday. But it's just the same example, only that I've simplified it. So let's just have a look. Again, this one is an example on predicting the house price. But in this case, we are going to be checking just one dependent variable and one independent variable. So the problem statement in this one, we are told that given the above data set, I think the data set that I've shared, there is two data sets that I've shared in the group. There is one on area price, and there is another one that has four variables. So you're going to start with the one with area and the price variable. So you're saying, given the above data, build a machine learning model that can predict home prices based on the square feet area. So in this example, you're going to use the data set with area and the price. Uh, there is an equation that I was talking about on the linear equation, whereby we say that we have y is equals to mx. I think I can just write this below here. So there is this y is equals to mx plus a constant. Most of us are familiar with this equation, right? Dickens, have you ever seen this kind of an equation? Any person who is not familiar with this equation, that is y is equals to mx plus c. I think this one is an equation that you guys did in basic maths, where we have m as the coefficient, and we have c as our constant, and then we have the intercept, which is y. So that is the same concept that we are going to use here, because you are saying that we have home price is equals to the coefficient, and then times the variable that you are going to be checking in here, or the variable that is, or the feature that is determining the house price, and then we are going to add this constant. It's just the same as this one. So y is equals to mx plus c. Because again we are dealing with a linear from the word line, linear regression model. So I think having said that, this is the equation that we are going to use, and I'll show you how it is applied. I think we can first start by importing pandas as PD, and then we import numpy, and then sklearn, we import the linear model that you're going to be using. And for plotting, we can import matplotlib.pyplot as PLT. So after doing our importation, I think you can just run these and ensure that your code is running. The second step is to import our data. Not import our data, but read our data, the CSV file. And In this case, I think I've changed the name of that file. So I think I can also upload mine here. I'm referring to this dataset that is called home prices underscore one. This is the dataset that I want us to use for this example. So I think I can just copy the path and just check if we have our dataset. And you can see we have our dataset. So it is the area of this area is in feet squared. I think there is somewhere we have written that it's square feet, the square feet area. So it is the area that the house has been built that is going to determine the price in this case. And if you can just check these, I think the bigger the area, I think the higher the price. You notice that we have the highest area is 4,000, and you can see also the highest price is 72 725,000. So there is that relationship between the price and the area. So meaning that the higher the area or the larger the area, the higher the price. So there is that linear relationship between the area in which that house is built and the price. So so with this data, we are supposed to create a linear regression model that will enable us uh, to predict the price given area. So that is what we are going to be doing in this example. We are going to have examples of a given area. You find the price now using the model. So I think up to that point we are good, and we can just start by drawing a scatter plot. And the scatter plot here, you're going to draw a scatter plot of price versus area. So, and our x axis will represent the area, and the price will be on the y axis. Uh, to draw a scatter plot, I think we have already learned these. So it's PLT and then dot scatter, and then we are going to pass our x and y values. So in this case, the x value is df dot area, and the y value is df dot price. And then we have the color. You can set the color. These are just attributes, and even you can just set the marker for your for your points. So in this case, I'm just using a plus as a marker, but you can use any other marker that you want. So this is the kind of scatter plot that we have, and you notice that these points, like 4 points here, they are on this is where you were just told, like you draw the line of best fit, right? And the line of best fit is the line that at least passes through most or touches at least most points, right? So you can easily draw a line of best fit based on these points. So, but in this case, I don't think you are going to draw that, but you can at least see that at least 4 points here. You can draw a line of best fit that at least touches 3 points or four. So I think that is it. Just showing that is the graphical representation of the points that we have in here. And from this point, I think we can just I don't think this one is relevant, but this is the column that you are going to use to predict. I think I just wanted them to be to have that to drop the price so that I can at least be left with the dependent column here, which is this in this case is the area. And also I have the other I have the other column here, the price. So these are just the two columns that I'm going to use to create a linear regression model that will enable me to do a prediction. So after that, we are supposed to create a linear regression object, and I think I showed you how to do that. And I think I can just call this one I can just call it linear regression uh, bj to main object. Or what I was saying, that you create an instance, creating an instance of the linear regression, or what we call the object. So it is linear regression model object is equals to the linear regression model, the one we imported here up. This one is the one that holds our model here, the linear regression model. So dot linear regression. I think having created that object, we can now fit our model. Or fitting just mean to train your model. I think you can just call that now our linear regression object, which is linear regression underscore object, then dot fit method. This fit method is the one that is going to help us to do the training of the model. And we want to train our model with the new DF. And our new DF, what is our new DF? Our new DF is the area, and we're also going to pass the price. So after running this, let me see that. What is it saying? The DF is not defined. I think we should have run these and also these. Good. So if we now run this, we are now supposed to get an error. So now already now we have a train model because we have fitted our model with data. So there is something that I was saying, that you can check the accuracy of the percentage accuracy for this model. And in this case, you're just going to check the score. And the score, again, you are going to pass this data because we have not divided our model. We have not divided our data into train and test. In this case, we're just using the whole data set. So let me just have that. It's linear object. You can just check that and see. And you can see that the accuracy for this model is it will now be 90. It's expressed in form of decimal. So this one is supposed to be 95.84% accurate. I don't think this one is relevant at this stage, but we are going to test this when we have at least large data sets that we are going to divide into train and test data set. But in this case, we're just using the whole data to train the model. So after that, after now having our model, we can now predict the price of a home with an area of maybe 3,300 square feet. How do we do that? We are just going to invoke our model, or call our model here, which is linear regression underscore object. And then we have a function that is called predict, and then we pass the area for our the area the area of our home. So, and in this case, we have the area of the home is 3,300. So if you were to run these, we are going to get that is 62, that is 628,715. But how did you arrive at this? How did you arrive at this? It's simply by using the equation that I explained uh, somewhere here up. Hereby that we are saying that home price is equals to the M, which is the coefficient, we multiply by area, and then we plus the constant. But are we able to determine the M and B in our equation, in this equation? Yes, we are able to do that. We should be able to do that because we're just going to call our model here, which is linear. This linear regression model, and then you are just going to we just need, I think I should add something here, check in the coefficient that model uses. So by just invoking your model here, and you just use the dot operator and then the coef underscore to check the coefficient that is used. So if I was to run this, the coefficient that is used is 135, no, 135. That is 135 dot 78767123. Can you also check the can you also check the intercept, or what are we are calling the constant? We're just also going to invoke our model here, that is linear underscore, and then we just dot intercept underscore. With that, we should be able to get the intercept that is used. I think this one should be linear underscore regression object. Good. So from that point, I think now we can now use this. We can now use this equation here, whereby we have y is equals to m, and already now we have m, which is our coefficient here, and we have our b, which is our intercept, to find y, and the y in this case should be the home price. I think we should maybe edit these, and let me just have this one as home price is equals to, yeah, I think that one now makes sense. Yeah, home price is equals to m times x plus now b, which is our intercept. And we can, I think, we can use those values. We are checking the price of the house that has 3,300 square feet. So we can take that. Um, Let me just take that. So what is our coefficient in this case? Our coefficient is this value, which is 135 dot and some decimals there. So I think you can just copy this, copy, and say that home price, you can just call it home underscore price is equals to the coefficient. We multiply this by the area, and the area is in this case is that 300 plus our coefficient. No, our intercept. Our intercept is this value here. So copy plus this value, and if we just print this, let me just print this home price, home underscore price. We should be able to get the same value, this one, and the value that you are getting from our model here, they should be the same or almost the same. You notice that in this case you are getting it, the house price is 628,715, and also you are getting the same as this one. Any question up to that point? Any question? Was I fast? Are we together? Thumbs up if you're together. Who thinks that we should repeat that? Any question up to that point? Wherein a person who is who wants clarification. Lewis, are we good up to that point?
Yeah, yeah, good.
Okay, okay. What about Mariwa? Is Mariwa in today? Rose, are we good? Someone is asking if I'm recording the class. Yeah, I'm doing the recording. I'll share it after the class. So I think that is how linear regression works in its simplest form. Because you notice that to determine the price of a house, there are so many factors to consider. It's not just the area under which the house is built. But I just decided to start with one variable. To start with one variable determining the price of the house. And even you can have another example, like predict the price of a home with the area of 5,000 square feet. Again, now using the model, you can just invoke your model here, linear regression object dot predict, and then you just pass in your value. So with this you're able to calculate the price of the house based on the area. I think that is it. I think that is it. You can even pass a CSV file with areas, and even try to do the prediction. It's just quite easy. You're going to read the CSV file and even do the prediction. So I think that is that with that example, and you're going to have an exercise whereby I'm going to share with you a data set. But this one is just this one is just an exercise. You can do it at your own time. It's just here, predict Canada's per capita income in year 2020. Like an yeah, in the year 2020, we are told I'll share this. I'll share the GitHub link for this one, so that you can give it. You can just try it. Um, I think now we can move to an example where we are going to have more than more than two features determining the price of the house. Let's just check that. Yeah, I'll share this file with you. So let me just I think I'm also going to upload the second data set here to manage sessions. So I think you can do already this one. Let me upload this data set. So in this case, we are going to determine the price of a house using the area, the number of bedroom, and the age of the house. So let me just upload that data set. Let me just copy this, copy path. So the first thing is always to import the required um, libraries. And then the second thing is to import your data set. I think you guys are familiar with that now. And you notice that now in this case, we have a missing value in the bedroom. I think as I was marking your last week, but once assignment, I think we had an issue with the filling these null values with maybe given values. But we are going to see how we do it in this example, because I think we have a null value here. And so you can see that we have three features here that are going to determine the house price. This value here, this null value here, we are going to fill it with median of this column. And how do we do that? It's just by calling your df, and then you specify the column that you want. In this case is the bedroom, so you can you use the df dot bedrooms and then the median, and you are getting the median as 4, right? So this null value, we are going to fill it with 4. So how do we do that? How do we do it? After calculating the median, you just have to use the fill num method. So you're just going to have the df dot bedrooms, and then is equals to df dot bedrooms dot fill null, the null value with our value here. I think we can call this one median. Median value underscore value is equals to this, and instead of passing a whole logic here, we can just pass in this variable. So it is median value. You can just rerun this, and now if I run this, you notice that the null value now do not exist. We have already filled that with a 4. So this is just the data set that we are going to use. And also you are going to use the linear regression again to predict the price of a house based on these features. So how do we do that again? We just have to create an object. We create an object or create an instance of a linear regression model, and we are doing that by, let's just call this one linear underscore regression. We can call it model, and then we can just now fit or train our model with that again. So linear, just here. So how are we doing this? How are you doing our fitting? You notice that in here, when fitting, we are calling the df dot drop the price, because we want this price to be a feature on its own, because this one is this is the feature that we are trying to determine. So we want to drop that price. We want to drop this price from the data set, and that is why we are using df.drop price. And also we want to drop our columns, that is axis columns, and then we just now pass the price, because we said that fit function takes two arguments, right? I think we said that last week. The fit function takes two arguments. That is the x train and the y train. So in this case, we have our x train as the other features. These features, that is the area, bedroom, and age, and we have our y train as the price. So and that is why we are passing in these two values here. If you were to run these, you notice now we have a train model, and also you can check the score. You can as well as check the score, the accuracy score, by invoking again this model dot score, and then you're just going to pass these values again. Uh, that is the X test and Y test. But in this case, we don't have the test data because we have not divided our data in train and test, simply because we have a small data set. Um, so after doing that, I think you can also check the coefficients. We have the linear regression model. We check the coefficient that is used. And in this case, we are going to have three coefficients, simply because we have area, we have bedroom, we have age. So our equation here looks like this. It's like now y is equals to maybe mx1 mx1 plus mx2 plus mx3 mx3 plus the intercept, because we have three different uh, dependent variables. That is the area, we have the bedroom, and we have the age. That is why we have in mx1, mx2, mx3. But you notice that mr are the same, the coefficients are the same. So the other thing, we can just check the intercept. The intercept in this case is just one, because the intercept is the one that we are trying. We just have one intercept. That is the C. We just have one C. So we can have it as linear. You can just check that. And we have this value. So we have our coefficients, and we have our intercept, and therefore we can now, using the equation, this equation here, we can calculate, we can predict a house, or you can just directly predict using the model. So let us just try to predict using the model. So linear underscore regression underscore model dot predict, and the house we want to predict is the price of the house that we want to predict is a house with 3,000 square feet area, a house that has 3 bedrooms, and a house that is 40 years old. And that is that is the data that you are going to pass to predict this. So if we run these, we are supposed to get the price of that house, which is in this case is about 498 498,408 and some decimals. So that is how we this is the price predicted for such house. And you can predict the price of any other house, provided that you have these three variables: the area, the bedroom, or the year. Um, you can as well as calculate that one manually using the coefficients and the intercept. And again, you're going to get just the same value. or almost the same value. Yeah, I think we have it, we have it here. Again, we have 498, 408. Then we have some number of decimals there. With that, you can predict now any any price of any house price based on based on those three based on those three features. So any question? I think as I should change this one to a linear regression model. So any question? Do you have any question, suggestion, or comment? Nathan, are we good? We have Eileen. Eileen, are you good up to that point? Eileen, is it Eileen? Mariwa, are we good up to that point?
Yeah, yes, you are good.
What about Faith? I think Faith has never spoken in this. I've never. Faith, I think I saw Faith somewhere. Um, I think that is it with the linear regression. So if you understood that, then the question that you were doing on Thursday, it shouldn't be an issue, because as we add the number of features to do the prediction, uh, the model tends to become complex, like the one we were doing on Thursday. Was it on Thursday? Yeah. Also, this one has we have an exercise. I think these are things that you can just do it for practice. In here we have I'm going to share with you the hiring data. And we just try to create a machine learning model for HR department that can help them decide the salaries for future candidates. That one again will be based on the years of experience, maybe the score in a test may be given, and also the score on an interview. Because these are just the things that are being used, maybe even to determine whether you're going to be hired or not, based on experience, based on the score that you get in a test, based on the interview score. You know, those are some of the things that will determine even the salary that you're going to get. So I'm going to share with you another file, a hiring CSV. and then you can just try to create a HR department model to predict salaries for future candidates. Um, and then if there is no question, then I think we should have the last example. I like teaching each model at like per lesson. We just work with one model rather than introducing multiple models. So again, we are going to check the file that we had on that. This one is quite complex. So let us just check it. It was on a linear. It was on a regression. Let me check that. This one was quite complex because we had a large data set, and we had to divide this data set into train and test. And again, we have several features that it determines the house price, right? But the approach is the same. But this one has a bit of data pre-processing. So let us just check this. We just have to do the importation. I think you are quite familiar with these. So importing NumPy, Pandas, Matplotlib, you import the Seaborn. So let me check if I have this data set here. I think I don't have it. So let me just upload this. So I think we already have it now. So we have, this is reading your data set. And I think if I can run this, I should be able to get the data set here. This is just an explanation of what you expect in your data set. The AVG, area income, average area house age is house age, basically house age. We have the number of rooms. We have the number of bedrooms. We have the population, maybe in that area, and we have the we have the column that has the price, and this is what we are going to be predicting now based on these five variable features. You can call them variables or features. So I think we started by checking the head of this data set just to familiarize with the data set. This is the kind of data set that we have: the area income, the house age, and all these are just average income, average house age, average number of rooms. That is where you can see that in the number of rooms we have some decimals, because it's just an average of that. So we have the area of the population, maybe in the area where that house is built. and then this is the price column, or the column that you are going to be predicting based on these other five. We said you can also check the statistical summary. No, not the statistical summary, but you can just check the general information of your data set by the info. You can have the describe to check the statistical information about your data set. And in here, you're just going to get the count, the mean, you have standard deviation, mean, the quartiles, and even the maximum, value in each column. I think we were in this case now, because we have so many variables to determine the price. I think it's just quite. I think we can draw a scatter plot for all these variables, like each variable the price, each variable the price, each variable the price. So you can just simplify that by maybe drawing a distribution plot. I think we did that. Yes, I just want to start from where we have the training our linear regression model, because this is where again we must do some data pre-processing. So in here we are just going to have the x values, and also we are going to have the y values. So if you were to check this data set, there is a column here that is called the address. The address might not affect or address cannot affect the price of a house. So we are going to drop this, and we're just going to use these five columns here. That is the income, the age, number of rooms, number of bedrooms, and the population. And that is why I want to drop that address column in here. So I'm just going to have an X, which is our new, will hold our new variables or our new columns, or the columns that you want to use. That is the df, and then I just pass in the columns that I just want to use. So you notice that I've omitted the address, and the y is the column that you are going to be predicting. That is the price. So after that, you notice that our data set here, if you were to check, let me just, instead of having this here, I think you can have df dot shape. So it should be just shape, not function. The df dot shape is just telling us that we have 5,000 entries of data, and we have 7 columns. So in these cases where we have large data sets, for you to create an effective model, it's always advisable to divide your data set into train and test data set. And that is what we are going to do in here with the help of train underscore test underscore sprint. This is what is this attribute is the one that is going to help us to do that. Like we want to, some of the data, we use it for training, and the rest we are going to use it for testing our model. So how we do that is just importing from sklearn.model underscore selection. We import this train underscore test underscore sprint. So after importing that, we're just going to have four variables, whereby you're going to have x train and x test. We're also going to have y train and y test. You notice that in the previous examples, we just had x and y, but in this case, we're going to have four variables simply because we're going to have like x's for test and the y's for train. So adding up to four variables. So x train, y x test, y train, y test. So that is equals to, now we are going now to use the train underscore test underscore sprint. And then what are we going to pass? You're going to pass our whole now data. That is the x and y, and even we specify the ratios to which we want to divide our data set. So in this case, I'm just going to specify the test size, which is 0.4. And if you guys, you can remember very well, I said that 0.4 represent 40%. If you were to convert this one to percentage, it should be 40% will be used in test. But you can use even 0.2. This one is always upon you to, it's upon you to choose the value that that you want to use here. But you should also choose carefully, because this one can affect the accuracy of your model, especially if you are going to use just a small percentage in training. It's always advisable that you have you use the test size uh, to be small and the training data to be more, because now if I use the test size as 0.2 here, so I'm remaining with 0.8 for training. And then you're just going to have another attribute that is called the random state, which I'm just setting it to just a random value. So I can just run, like I can run these and also even run these. I think having run that successfully, then from there I should go to create our model here. Just have that run as creating model hash, creating model instance. So whereby I'm going to use the linear regression again, and I'm importing that from sklearn. Um, so let me have it as LM in this case, which is equals to the linear regression. And then I'm going to pass in my training set. That is the X train and Y train. So I think I can just run that. And this is where now you can just check the score, the percentage score. Was to run these. You notice that I'm getting a 92% accuracy score. So what if let me just try to change something here. I want to change something here. Let me, for instance, change this one to something like 0.8 for test. So meaning that the training will we will use 0.2. I just happen to run this, and I even run this again, and check the score. So did you notice something? Let me just use this 0.2. This one. And let's just check the score. So you notice when we use a 0.2 for test, we are getting an accuracy score of uh, of 92. But if you were to increase this to maybe something like 0.9, and we check the score here, you notice that our score has reduced. So these, among other factors, affects the accuracy of your model. And you always like the aim here is always to have the highest score, the highest accuracy score for your model. Because if you have, let's say, an accuracy of maybe 0.661 or maybe 60% score, you might not be able to make uh, the right prediction or the correct predictions. So among the changing the test size, maybe having that test sizes uh, to be a large percentage, and other factors, including not cleaning your data set, will always affect the accuracy of the percentage accuracy of your model. So you should always be keen on the number that you are putting in here. So let that remain to be 0.2, and run that one to be 0.2, 0.92, which is 92%. You can also use this print to check the intercept, and also you can check the coefficient. I think you should have before let us just have the coefficient here, but I think you already have the coefficient here below here, whereby I'm just presenting these the coefficients and how they affect the price of the house. I just decided to use a data frame to present this one as a data frame, so that I can have the column names, and I can have the coefficient for each column. That is why I'm just using the lim dot coefficient and the x columns, and I'm setting the columns to be the I'm just setting the column here to be the coefficient, which is just right here, so that at least I can have the coefficients for each feature. In this case, we have the area income as 2021. We are going to use the coefficient of 21.52. The area of the house, I'm going to use this coefficient. The area number of rooms, I'm going to use this coefficient. And the area number of bedrooms, I'm going to use this coefficient. and the population, I'm going to use this. So you notice in the previous example, we had we used the same coefficient, but in this data set now, we have different coefficients for each feature. We have a coefficient for each feature. So now to maybe calculate the price of a given house, um, you are going to use these coefficients, and the intercept will just be the same, because again we had our equation as uh, you can just have our equation here down. It's going to be something of this nature. You're going to have house price prediction. You can just call it prediction is equals to something like you're going now to have M1 X1 plus M2 X2, and you're going to have something M3 X3 plus M4 and the X4 plus M. This one is M5 X5 plus now the constant C. So this is the kind of an equation that you are going to have. The coefficients you multiply by the column values for you to predict this. The summation of this is going to give you the house price prediction. I think you can just I can just comment out that. So how do we interpret the coefficients now that we have different coefficients? So we are saying that holding all other features fixed, 1 unit increase in average area income is associated with an increase of this of US dollar 2156. So this is how now the area income is going to affect the entire price of the house. Again, when we come to the other feature, that is the area of the house. So we are saying that holding all the other features fixed, or what do we call it ceteris paribus, for those of us who have done maybe some economics, holding other factors fixed or constant. I think you are calling it ceteris paribus or something. So this is how the coefficients are going to this coefficient. These are how coefficients. These coefficients are going to affect the price of the house. These five coefficients. So after there, you can just, I think you can just try to do even a prediction. Let me see this. Are you using LM or we changed that to something else? And even we can just you can draw that scatter for the test, the y test, and even the prediction. And you notice they are giving us again something similar to that of a line, right? This one is linear. When you try to plot y-test against the prediction. So any question on that? Do you have any question? Steve, any question?
Nah.
That is how we use machine learning to do prediction uh, using just one model. This is just one model, linear regression model. So I'm waiting for any question about linear regression model. And if you are to get back to the notes on the introduction of machine learning, you notice that what we have been doing is what we call supervised machine learning. Is all those examples they are part of supervised machine learning. So, do you have any question? Suggestion? Lewis Gatimo, any question?
Following the rule.
So, I think by now you should be able to tackle any question on linear regression models. There are also, just to mention, there is something we call the regression, or the linear regression evaluation matrix. If there is no question in the implementation, so you can check. Even here I've tried to do a distribution plot again. You will just check that. So let me just say something on the regression evaluation matrix, and then we can just call it a day. Um, we say that there are three common evaluation metrics for regression problems, and we have something we call mean absolute error. And we define mean absolute error as the mean of the absolute value of errors. And this one measures the average absolute difference between the predicted values and the actual values. And we are saying that it is less sensitive to outliers compared to MSE, or what we call the mean squared error. I think that one is uh, it's quite simple even to understand. And this is the formula to calculate that. You're just saying that you cannot like predict, you cannot like predict 100%. You cannot have a prediction of 100%. So there is those errors, right? And that is what we are trying to say, that you can calculate the mean absolute error, which is the difference between the predicted values and the actual values. So it's a way, it's an evaluation matrix for a linear regression model. And this is the formula for doing that calculation. You just check the actual values and the predicted values. Just check the average. You just check the average. After doing the difference, you do the average. And we are saying that it cannot be compared to, it cannot be it cannot like it's less sensitive. I think those are the best terms to use. It is less sensitive to outliers compared to the MSE, because you notice that when we come to the mean squared error, again, what we got here, it's kind of we are doing we are squaring that. So that is why we are saying, of course, you expect to get a larger value here compared to this one, because the mean squared error is the square of this. So we are saying that it measures the average of squares of the errors between the predicted values and also the actual values. And we are saying it penalizes the larger errors more than smaller ones. Of course, you cannot compare when you have a larger squaring a larger error and a small error. So that is why we are saying that it penalizes larger errors more than the smaller ones. The other evaluation matrix is something we call the root mean square error, or what we call RMSE. SE is the square root of the mean of the squared errors. And we are saying that RMSE is the square root of the mean of the squared error, providing a measure of the average magnitude of error. It is the same as the unit. It is in the same unit as the target variables, making it easier to interpret. So the root mean squared error, the square root of this now. And there is a way we do that. We from the scale, and you can have a problem that it requires you to check the metric, to calculate the matrix. And I have how we do it here. We're just going to import a matrix from sklearn, and you notice in here we're just using these formulas here. It's just these formulas that we are using here, because we're just invoking the matrix, and then we just call the mean absolute error, and then we just y test and the prediction. Also, when it comes to the MSE and even the square root for the RMSE, the square root for MSE, and we have those values here. Maybe in some problems you are going to be to calculate this if asked, but this is the math behind that. Don't think I have to explain the formulas. So any question? I think that is the end of our discussion on the linear regressions models in machine learning. So do you have any question?